Hello, everyone. Today I'm going to start a new topic that I think will be very interesting to many of you, which is the imaginary numbers. So, what are imaginary numbers? Most of you already know that we use the letter I. Some people use J, but I as the square root of -1, right? Okay, so now we are going to look at I. Square root of -1 is called I. And you say, how can you get the square root of -1? Well, it's imaginary, right? But we'll see that if you multiply it by itself, you get I square. It's the same as multiplying -1 by -1 under the root, so you get -1. So we know that uh, I square would be -1. If you multiply by I again, then you get -I. And when you multiply both sides by I again, you get I to the fourth equals 1. So basically, it's you can see that if I tell you I to the 100, all what you have to do to find its value is to divide the 100 by 4. And since you don't get any remainder, it means that I to the 100 is 1. If you get a remainder of 1, you get I. If you get a remainder of 2, you get I squared, which is -1. If you get a remainder of 3, you get -I. And if you don't get any remainder, then it becomes 1. So we know all of this. That's easy. We know that we can create complex numbers. So for example, usually we refer to the letter Z for complex numbers, and I say Z equals 3 minus 2I. So it has a real portion, so that's complex. It has a real portion, and even this has a real portion, which is 0, right? So you can always think of imaginary numbers as complex numbers. And this portion is the imaginary. Okay, so now I can add two imaginary numbers or subtract them very easily. I'm going to add the real parts separately and the imaginary part separately. But when it comes to multiplication and division, that becomes a little tricky. And then we'll see how we are going to look at that from the point of view of geometry. Did you hear geometry? Someone say geometry? Yes, I did. Okay, so let's assume we call this Z sub 1, and then we get another number called Z sub 2, which is, for example, -2 plus I. And I tell you, find Z1 times Z2. So it's so easy because what I'm going to do is to say 3 minus 2i, and then I'm going to use the same logic I used with multiplication, -2 plus I. Meaning, I'm going to multiply the -2 by the -2i, and then by the +3, and then I multiply I by that and I by, like when you multiply tens and ones, for example. So let's start with the -2. Negative times negative is positive, and 2 times 2i is positive 4i. -2 times 3 is -6. And then I'm going to go to the I. First of all, I have -2 times 1 is -2, but I times I is I square. What did we say I square is? Is -1. So this times this is negative, times negative is positive, times 2 is +2. And finally, I times 3 is positive 3i. So the answer is -4 plus 7i. That's the multiplication of these two. And we'll see what this means later. Now let's do Z1 divided by Z2. Meaning I want to say 3 minus 2i divided by -2 plus I. And here we have a problem. because I don't know how to divide 3. I can, but it's so complicated. It's much easier if we multiply top and bottom. Remember, suppose instead of having -2 plus I have √3. What do you do to get rid of that? Don't we multiply top and bottom by √3? So the √3 and the √3 cancel each other. Or if this was -2 plus the square root of 5, I multiply by what? What did we call the conjugate? To get rid of the square root in the denominator, we do the same thing here to get rid of the I. So we multiply by the conjugate of this number, and the conjugate of this number is -2 minus I. So -2 plus I, its conjugate is -2 minus I, and I'm going to multiply top and bottom by that. I already did this. I'm sorry. Yeah, we did that for plus I, but we didn't do it for -I. So the multiplication, I'm going to do it the same thing as before. So I'm going to say 3 times -2 is -6. 3 times -I is -3I. -2I times -2 is positive 4I. And -2I times -I is positive 2. I'm sorry, is -2. Why? Because negative times negative is positive, and I times I is -1. So you get -2. So you get the numerator becomes -8 plus I. But what about the denominator? Remember when we had a difference like a plus b times a minus b? We say it becomes the difference of two squares. In the case of I, it becomes the positive of two squares. I'm going to remind you of something we did earlier. Remember when I told you that if you want to break this or factor it, you say a minus b times a plus b, right? But what about a square plus b squared? We said you cannot do it with real numbers. So the way we do it is we say it's a minus bi times a plus bi, or ib. Some people write the I in front, it doesn't matter. And that's what I have here. Just saving time. So when I have a complex number multiplied by its conjugate, the product gives me the sum of the squares. -2 squared is positive 4, and 1 or -1 squared is positive 1, so I get 5. You can do the math and find it for yourself. Let's do it just once, and after that, when you see a number times its conjugate, or a complex number times its conjugate, take this coefficient, square it, take this coefficient, square it, and add them up. It's much faster. But let's do it. -2 times -2 is positive 4. -2 times -2i is positive 2i. I times -2 is -2i. And I times -I, the negative, and I squared is -1, and negative times negative is positive, so +1. These two cancel, and you get 5. So it's a faster way to do it. So now we know how to add, subtract. We didn't do addition and subtraction because it's trivial. We did multiplication and division. Now, the next step is to say, and then what? What else can I do with imaginary numbers? Maybe first I should show you that we can represent it graphically or using geometry or trig, as you will see, by drawing a circle. And we are going to assume, well, we didn't have to draw the circle, but I'm just, because later I'm going to use it. So here is my x-axis. Oops. My x-axis would be called the real axis. And the vertical axis, which we use as the y-axis, would become the imaginary axis. or I am. Now, if I have to represent, say, z1, which is 3 minus 2i, I'm going to use as if this is the x and that's the y, right? So I go 3 positive to the x and 2 negative to the y and get a point, and so on and so forth. But that's not what we are going to do now. Let's wait for a second, and then I'm going to draw your attention to a session I did on expansion of trig functions like the sine, the cosine, and also we did the e to the x. Just quickly, I'm going to write them down without deriving. I'm going to say we did the cosine of theta. We used x, but it doesn't matter what variable you use. And this was 1 minus theta square over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on and so forth. We also found sine of theta to be theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7 over 7 factorial plus. And finally, we found e to the x, or here we can say, gonna say e to the theta to be 1 plus theta square over 2 factorial plus theta cubed over 3 factorial plus till infinity. And we said that there is something here. I can see the 1, I can see the theta, I can see the theta square over 2 factorial. Oops, but the sign is not the same. I see theta cube over 3 factorial, but the sign is not the same. But then I will get theta to the 4, theta to the 5th, and then 6 and 7, the sign will not be the same. And we notice that if I make this e to the I theta, then I will get 1 plus I theta, and then here it would be plus I square, which is negative 1. So that would become negative theta square over 2 factorial. I fixed this guy. So now I have the 1. I fixed that, but I messed up that. Let's continue and see if we can fix the other one. And then I have, when I multiply that, I theta cube is I cube, which is negative I theta cubed over 3 factorial. And then plus I to the 4th, which is 1, theta to the 4 over 4 factorial, which is this guy. And now I see that the 2nd, the 4th, the 6th, the 8th, all of them would be messed up. But when I look back here and I say, oh, what if I make that, what if I multiply this equation by I? Why? Because if I multiply by I, not sine of I theta, no, I outside, meaning this would become I theta, oops, now they are the same. This would be I times theta cube over 3 factor, oops, they are the same. And next one, and next one. So now I can say e to the I theta equals cosine theta, which I left as it is, plus I sine theta. That's a very powerful expression because now it gave me a way to go between trig and e to the I. But let's go back to the circle we did. And let's assume this circle has a radius of 1. So it's a unit circle. Okay? And then I have a point here. This point means this radius is 1. So that distance is 1. Okay? What would be the horizontal portion and what would be the vertical portion? We learned from trig is that if I drop a line like that, perpendicular line, and I say this angle is theta, and we know that the cosine of theta is adjacent, which is this portion, over hypotenuse, but the hypotenuse is 1. So this would be called cosine theta, right? Because cosine theta is this guy divided by 1, but this, when you divide by 1, you get cosine theta. But for the same logic, by the same logic, the vertical would be, would it be sine theta? No, that's the imaginary number. So this is I sine theta. So this point right here has coordinates cosine theta and I sine theta. But cosine theta plus I sine theta is called e to the I theta. So I can represent it as e raised to the power of I theta. So let's take that for a second and say, this is so confusing. I don't understand. Okay, let's put theta equals 0, meaning this line coincides with this line. So the cosine theta would be 1 and the I sine theta would be 0, right? So this should be cosine 0. So from here to here, cosine 0 plus I sine 0. Sine 0 is 0, cosine 0 is 1, so that would be 1. Yes, it is 1. It's the radius on the real axis, so we call it 1. And what is e to the I 0? Well, anything 0 times I is 0 and e to the 0 is 1. So we know this is correct. Now let's go and say theta equals pi over 2, meaning this line. So I would say this length would be represented by cosine pi over 2, which is 0, plus I sine pi over 2, which is 1. So you get 0 plus I times 1 equals I. Yes, this is I. And if I say e to the I pi over 2, I get I, because I multiplied the angle by that. Let's take a last one, because that would show us the Euler very important theorem. If I say theta equals pi, meaning I'm here, what do you expect the value to be? That's the real axis, but I'm going to the left. Let's see. Cosine pi plus I sine pi. Like we said here, cosine pi over 2 is 0, sine 0 is 0. Also, sine pi is 0. So you get cosine pi, which is -1. And here comes the very important equation. E to the I pi, because this angle is pi, equals -1, or some people say +1 equals 0. And this is Euler's equation. Have you? Tell me the truth. Did you expect to see E, I, and pi in the same equation, a very nice, simple equation like that? The first time I saw it, I didn't expect. I say, what does pi have to do with E, with I, and all of that turns out to be equal to -1, meaning e to the I pi equals -1. Or the way we write it usually is that. So far, so good. Okay, but okay, nice, but what am I going to do with that? It turns out that we can do a lot of stuff. For example, somebody came after that, de Moivre, and de Moivre came with a theorem that says, notice that if I take cosine n theta plus I sine n theta, that would be the same as taking cosine theta plus I sine theta and raise the whole thing to the nth power. And you say, Okay, nice mathematical, complicated equation, but I don't see where I will need that. Say, okay, I'm going to leave it for a second and go and just talk about something else. No, I'm not confusing you. I'm not doing anything. You will see how I'm going to relate back to that. Now, when we get um, any, in fact, vectors are the same, but we are going to look at any number z, and let's pick an easy one. So let's say 3 minus 4i, for example. Why easy? Because now if I ask you, what is the magnitude? It's not a magnitude, but we call it the argument. The argument of z, or arg of z, is basically the length of that. So instead of having a unit circle, suppose I just go 3 units to the right and 4 units down to get 3 minus 4i. What would be the distance from the origin to the end? You say, Pythagoras. That's what I remember. Yes, you would be right. So we would say the argument would be the square root of the 3 square plus, always plus. I see people say minus 4 square. No, 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 no. Argument cannot be so the quantity under the bracket cannot be negative, meaning it cannot be imaginary or complex. No. So plus negative 4 quantity square. It's the square root of 3 square plus 4 square, or the square root of 9 plus 16, or the square root of 25, or 5. So the argument of this thing is 5. So I can write z as 5 times, that's only 3. Yeah, if I multiply out by 5, I divide inside by 5. So if I write it like that, this would be represented as r, which is the argument, but we usually refer to it with the letter r. 3 over 5 here, check it for yourself, would be the cosine of theta, plus the 4 over 5 is the sine of theta. And why is it negative? It is negative because 3 minus 4i is in the fourth quadrant. First, second, third, fourth. I go 3, 4. In the fourth quadrant, the cosine is positive and the sine is negative. Yes, it is positive and this is negative. In fact, I can say also that theta, in this case, I can say it's arctan, or the angle whose tangent is negative 4 over 3. Or I can say theta is arc sine 3/5 or arc cosine, arc cosine 3/5 and arc sine negative 4/5. You can do any of those. But now there is something very interesting. I can take powers of z very easily by using de Moivre's equation. So for example, let's just take it one step at a time. I want to take 3 minus 4i and square it. Look here. This angle is cosine theta. So I can say, I know that cosine theta is 3/5. We already found that here. So it's 3/5 minus 4/5 I square, but I divide by 5, so I have to take out 5 squared. So I can rewrite it as this. Again, what I did, instead of taking 3, I multiplied by 5 and divided by 5. So I get 5 times 3 over 5, but I have a square, so when I take it out, it becomes 25. And now, if I want to do the math, I say, well, it's 5 squared, that's a constant. 3/5 was cosine theta. But now I have to multiply by cosine twice theta. I don't know cosine of twice theta, but this basically, if I know the angle theta, I would write it like that. In fact, we can complete the work and find cosine 2 theta. You can find it. You can find sine 2 theta because it's 2 sine theta cosine theta. So you multiply 2 by this, by that, and substitute. You will find that it is the same. But now, even if we leave that for now, I don't really need it. But if you want, just for the sake of it, I know that this guy is cosine square theta minus sine square theta. That's what you learned in trig. Cosine square is 9 over 25 minus the sine square is positive now, minus 16 over 25 equals negative 7 over 25. And the sine 2 theta is 2 sine theta cosine theta. So it's 2 times 3/5 times negative 4/5. So it's negative 24 over 25. So now the answer here would be 25 times negative 7 over 25 minus 24 over 25i. The negative and the negative, I'm sorry, the 25 and the 25 cancel each other, and you get negative 7 minus 24i. So the square of this is that. You can try it. Multiply 3 minus 4i times 3 minus 4i. Notice that okay, 3 times 3 is 9. 3 times negative 4i is negative 12i. And then negative 4i times 3 is negative 12i. Negative 4 times negative 4 is positive 16. But times I squared is negative 1, so minus 16. And 9 minus 16 is negative 7. Minus 12i and 12i is 24i. You get the same result. Okay, but why go through all of that if I can do it easily like this? Now, what if I tell you, take the square root of this? How would you do it? That's the last thing I'm going to do now, and then we can think of it later. The square root of 3 minus 4i. You say, get out of here. This is so complicated. I have no clue. Okay. Let's do it in a very easy way. I'm going to say, let's assume this number is another complex number. I'm going to call it a plus bi. And then I'm going to square both sides. So squaring the left-hand side, I get, I know this is a little complicated, but I think once you get it, you will see that it's very easy. Now, when you square this, you get a square. Let's do the real portion first. You get a square, and then you get plus I square, which is negative b squared. So a square minus b square, that's the real portion. And then you have twice ab, so plus 2abi. So now I can write two equations in two unknowns, which are a and b. I can say a square minus b square equals 3. Real equals real. And 2ab equals negative 4. Dividing by 2, this would be negative 2. So now I have ab, so I can use substitution. For example, I can say instead of b, I write it as negative 2 over a. So here I have a square minus negative 2 over a quantity square equals 3. a square minus 4 over a square equals 3. Multiplying everything by a square, I get a to the fourth minus 4 equals 3a square. I'm going to move it here and say minus 3a square equals 0. Okay? So now I need two numbers that multiply to negative 4 and add up to negative 3, meaning a square and a square. I want to have a negative 4 and a positive 1. And when I solve, notice a is the real portion. If I say a squared plus 1 equals 0, you get a squared equals negative 1. So a is plus or minus I. I'm not going to deal with that. I'm going to say a squared equals 4. So a equals plus or minus 2. If a equals positive 2, then b equals negative 2 over 2, which is negative 1. If a equals negative 2, then b equals 1. So I have two answers. One of them is 2 minus I, and one of them is negative 2 plus I. Try to square them to check if you are going to get this back. If I multiply 2 minus I times 2 minus I get 4 minus 2I minus 2I plus 1. Minus 1, I'm sorry. Minus 1. Because negative times negative is positive, but I times I is I squared, which is negative 1. So you get negative times negative is positive, which is 4 minus 1 is 3 minus 4I. Yes, I did it. Try it for yourself. You get this equals that. And I say, but wait a second. Didn't the Moivre told me that I can say, where did we write it? We wrote it here. If I make that to the power of 1/2, meaning the square root, it means this becomes cosine theta over 2 and sine theta over 2. So when I square, the square becomes multiplying by the power. If I take the root, it's dividing or multiplying by the root. So now we can see something very interesting. Suppose I want you to find the square root of I. Say, what? I is already a square root of negative 1. How do I get the square root of I? Here is I, right? We said if we square it, you get negative 1. Oops, this was 90 degrees or pi over 2. When I square it, I multiply the angle by 2 and I got pi. If I multiply it by 3, I get negative I, which is 3 pi over 2. And if I take it to the power of 4, I get back to 1. Oh my God, so squaring would be doubling the angle. Cubing would be tripling the angle. By the same token, if I take the square root of I will be dividing the 90 degrees into 45 degrees, which means the square root of I, if I go here, this angle would be pi over 4. So I can represent it as cosine pi over 4 plus I sine pi over 4. It's root 2 over 2 plus root 2 over 2I. Wow, it didn't take 5 seconds. But then you said if it's a square root, notice that for complex numbers, you end up with two results. Here, we ended up with 2 minus I and negative 2 plus I. So is there another complex number that when I square, I also get I? Yes. Notice that here we said theta is pi over 2. And when we took the square root, we said theta over 2 is pi over 4. But instead of saying theta, can't I think of that as, instead of saying pi over 2, it's pi over 2, and then I added 2 pi, so I can say theta equals 5 pi over 2. And I can keep adding 2 pi's, but eventually I will end up with only one of two values. If I say theta equals 5 pi over 2, and I take the square root, then I'll be using 5 pi over 4, which is 45 degrees here. This vector or this complex number is also, when I square it, I should get I. Sine pi over 4 is the same as, I'm sorry, I am in the third quadrant, so that would be negative pi over 2 minus pi over 2i, and that's the square root. And finally, I'm going to give you another example. Suppose I tell you, find the fifth root of 32. I know that the fifth root of 32 is 2, but is it only 2? No. That's the only real root of 32. But there are 4 complex roots that would also give me, when I take them to the power of 5, they will give me 32. Same logic. Notice that 2 is on the real axis. So if it's 32, I take the fifth root, I get 2. Okay? But I can say that the angle, instead of being 0, is 2 pi or 4 pi or 6 pi or 8 pi. If you do 10 pi, you will get 2 again. You always have to have only 5. So I can use 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5. So the fifth root of 32 equals fifth root of 32. We said equals 2, that's one answer. Then it equals. Notice that I get 2, the 2, but it's multiplied by cosine 2 pi over 5 plus I sine 2 pi over 5. It equals 2 times cosine 4 pi over 5 plus I sine 4 pi over 5. And keep doing that. Let's use a calculator to see that. So just want to make sure yes, I'm in radians. So I'm going to say 2 times cosine 2 pi over 5 plus I sine 2 pi over 5. So it gives me some number. If I take this number between, maybe I should have had parentheses just to be on the safe side. Yeah, insert parentheses here. And a parentheses there, and take it to the power of 5. I got 32. And you say, oh, it's 32. Yes, that's approximation. Also, look at what we get. It's 1.3 times 10 to the negative 8, meaning divided by 100 million. That's an approximation in the calculator, but it's basically 0i. So now one of the answers is 0.618 plus I didn't see that, 1.902i. That's the second answer. And then you substitute 4 pi instead of 2 pi. So we can come here, change the 2 into 4, change this 2 into 4, and I get another answer. Oh, no, I'm sorry. Probably click the wrong thing. 4. I get negative 1.618 plus 1.1756i. And you can find the other two. It's just using a calculator. It's not a big deal. But they would be 2 times cosine 6 pi over 5 plus I sine 6 pi over 5, and then 8 pi over 5 over 8 pi over 5, which is a direct application of um, uh, the Moivre's rule. Because we said we can say that this guy equals 32 to the 1/5 times 1 to the 1/5. 32 to the 1/5 is 2. And 1 to the 1/5 is where you get from the unit circle. This is 1, and if you want to take the fifth root of that, you can say I'm going to divide this angle, which is 2 pi by 5. So I get 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5, which is another way to look at this equation. Or, oh my God, is here. This is 32 to the fifth is 2, and then the fifth root of 1 is these values. Either it's 1, if you are on the real axis, or 2 pi over 5, which is 72 degrees, 144 degrees, 216 degrees, and what? 216 plus 72, so 288. And that's basically would help you find the root of any complex numbers very easily. I showed you two ways, really. Remember, we said we can assume that this equals that, and then I took the square root and I ended up with two values, 2 minus I and negative 2 plus I. If it's the fifth root, for example, it becomes so complicated. So the Moivre's rule made it so simple by using this unit circle and just divide the angle by, if you are taking a fourth root, then you have 0, 90, 180, and 270, or pi over 2, pi, 3 pi over 2, and so on and so forth. Here we had fifth root, so we had to go 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5, along with the real. I know it was too much. Maybe I should have divided that into two videos, but I thought, just in one sitting, if you look at how these things were derived, where did we get this equation from? Remember, if you go back and check how we developed these um, expansions, when you use polynomials to substitute for sine, cosine, e to the x, and some others, how did that help us understand very easily Euler's equation? Where did it come from? Where is the pi coming from? Where is the negative 1 coming from? And so on and so forth. I hope it wasn't hard enough or too complicated, but please, if you have any questions, add those to the comments. I'll try to improve. I know it's like I'm just doing it to help students, and I hope I'm doing that. It's not getting you more confused. I'd like to hear your comments on that and wish you all the best. Eh, Hope to see you soon. Bye.